Welcome to part 6 and the final part of our online lecture. The photolysis of carbon dioxide to reduced carbon in organic matter and its subsequent reoxidation to carbon dioxide through respiration, decomposition and weathering is central to the organic carbon cycle. But there are other sources and sinks for atmospheric carbon dioxide. Carbon dioxide readily dissolves in rainwater and seawater and then undergoes rapid chemical reactions to other ionic forms of inorganic carbon. The oxidized carbon in these waters is chemically reactive and becomes involved in a number of chemical processes. Because they do not involve organic carbon directly, these processes are together referred to as the inorganic carbon cycle. The important reservoirs of inorganic carbon are the atmosphere, the ocean, sediments, and sedimentary rocks. The sediment and sedimentary rock carbon reservoirs consist primarily of limestone. Limestone is a rock composed largely of calcium carbonate. Carbon dioxide is continuously exchanged between the atmosphere and ocean. The distribution of sources and sinks of carbon dioxide is tied to the circulation and productivity patterns of the oceans. In regions of the ocean where high rates of primary productivity have created surface waters with low carbon dioxide diffuses from the atmosphere to the ocean. In other words, the net flow of carbon dioxide is down the concentration gradient, from regions of higher carbon dioxide concentration, in this case the atmosphere, to regions of lower concentration, the ocean. Conversely, upwelling regions, such as the equatorial Pacific surface waters, have high carbon dioxide concentration because deep waters rich in carbon dioxide, as a result of decomposition associated with the biological pump, have risen to the surface there. In such regions, carbon dioxide flows from the ocean to the atmosphere. Thus the oceans serve as both a source and a sink for atmospheric carbon dioxide. You can see this effect in this picture down here. In the light grey, we are seeing regions which are carbon dioxide sinks. Carbon dioxide from the atmosphere is being transferred to the oceans. And the equatorial regions, as you can see here in the Pacific and the Indian Oceans primarily, we have the oceans acting as carbon dioxide sources. The carbon dioxide from the ocean is being transferred to the atmosphere. In the oceans, inorganic carbon exists in a number of dissolved forms. When carbon dioxide dissolves with water, whether it be fresh water or seawater, carbonic acid is generated. So we have carbon dioxide plus water forming carbonic acid, H2CO3. The double arrow in this reaction indicates that the process can proceed both forward and backward. The rates of forward and reverse reactions depends on the concentrations of the reactants on the left-hand side and of the products on the right-hand side respectively. If the concentration of the reactants is high, the forward reaction proceeds fast, depleting the concentration of the reactants and enhancing that of the products until the forward rate matches the reverse rate. Conversely, if the concentration of the products is high, the reverse reaction proceeds more rapidly, and the products become depleted and reactants enriched until the rates balance. In other words, chemical equilibrium is rapidly achieved in such reactions. A similar chemistry applies with atmospheric carbon dioxide dissolved in raindrops, making them naturally acidic. Rocks exposed at Earth's surface undergo chemical attack from this rain of dilute acid, a process known as chemical weathering. crustal rocks are composed mainly of two types of minerals, carbonates and silicates. From this, two types of weathering arise, carbonate weathering and silicate weathering. In both weathering reactions, the products include calcium ions and bicarbonate ions. Silicate weathering also yields dissolved silica. This is the SiO2 that we see here, which together with calcium ions and bicarbonate ions is transported to rivers and ultimately to the oceans. Silicate weathering consumes twice as much dissolved carbon dioxide in the form of carbonic acid as does carbonate weathering. Note, we have the limestone here, the calcium carbonate, reacting with only one molecule of the carbonic acid in carbonate weathering, whereas the calcium silicate in silicate weathering is combining with two molecules of carbonic acid in silicate weathering. This fact will prove important later when we attempt to balance the carbon cycle. The back reaction of carbonate weathering is known as carbonate precipitation. This process can occur abiotically, but the majority of carbonate precipitation is due to marine organisms precipitating calcium carbonate as shells and skeletons. Notice that carbonate precipitation is the reverse reaction of carbonate weathering. This has the effect of increasing carbonic acid concentration, which leads to an increase in dissolved carbon dioxide, which leads to a diffusion of carbon dioxide from the ocean to the atmosphere. We can combine the equations that we've just presented for carbonate and silicate weathering and for carbonate precipitation to determine the net effect of these processes on the chemistry of the oceans and on the composition of the atmosphere. To do this, we simply add the equations by adding the left-hand sides of both equations and adding the right-hand sides of both equations, and then cancelling out terms that appear on both sides of the resulting equation. The net effect of carbonate weathering on land and carbonate precipitation in the ocean is zero, because the two processes balance each other out. Remember that I commented that carbonate precipitation was the reverse reaction of carbonate weathering. The situation is different for the weathering of calcium silicate minerals on land. First of all, calcium silicate minerals do not reform under Earth's surface conditions. Thus, the calcium liberated during silicate weathering ultimately leaves the ocean as calcium carbonate. So the combined processes of silicate weathering on land and carbonate precipitation in the sea lead to a net conversion of atmospheric carbon dioxide to solid calcium carbonate. This process serves as a net outflow of carbon dioxide from the atmospheric reservoir, analogous to the net outflow of photosynthetically produced organic carbon that leaks out of the organic carbon cycle due to sedimentary burial. If we look at these three reactions of silicate weathering, carbonate precipitation and ocean-atmosphere carbon dioxide exchange, the silicate weathering needs two molecules of carbonic acid, but the carbonate precipitation only liberates one molecule of carbonic acid, which is the reason why we need this ocean-atmosphere carbon dioxide exchange to balance the carbonic acid. But this results in a net flow of carbon dioxide from the atmosphere to the ocean. The net result of these three reactions is the conversion of our calcium silicate to calcium carbonate and silica, and the absorption of carbon dioxide from the atmosphere into the oceanic environment. Like the leak in the organic carbon cycle, the rate of conversion of atmospheric carbon dioxide to limestone by silicate weathering and calcium carbonate deposition is quite small, about 0.03 gigatons per year. Nevertheless, if left unbalanced, this flux would apparently deplete the atmosphere of carbon in about 20,000 years. Actually, this number is misleading, because we have not accounted for the fact that the various oceanic reservoirs hold more than 50 times more carbon than the atmospheric reservoirs hold. A reduction in atmospheric carbon dioxide creates a concentration gradient between the atmosphere and the oceans. As a consequence, carbon dioxide will diffuse from the oceans to the atmosphere until the gradient is removed. Thus the depletion time would be more like 1,000,000 years, the time it would take for all the ocean's inorganic carbon to diffuse into the atmosphere and react with silicate rocks. Although this characteristic response time is significantly longer than the calculated 20,000 years, it is still short in terms of changes in atmospheric composition and climate over geologic timescales of many millions of years. On such timescales, then, there must be a return flux of carbon dioxide to the atmosphere and oceans to offset this outflow. This figure shows the inorganic carbon cycle. It is similar to the earlier figure that I showed for the organic carbon cycle, and again the reservoirs are in gigatons of carbon and the fluxes are in gigatons of carbon per year. It is important that you are able to read this kind of diagram, that you are able to identify the magnitude of the various reservoirs and also identify the magnitude of the various fluxes. Notice seafloor dissolution here, which represents the transfer of material from the marine carbonate sediments to the oceanic ionic forms of carbon, amounts to 0.3 gigatons of carbon per year. Here we have the carbonate weathering that amounts to 0.17 gigatons of carbon per year, which is converting the carbon in carbonate sedimentary rocks again into the oceanic ionic carbon reservoirs. Over here we have something a little bit more complicated. This is bidirectional. We're having the conversion of oceanic carbon dioxide in the form of carbonic acid into atmospheric carbon dioxide. This transfer amounts to some 60 gigatons of carbon per year, but there is also a transfer of atmospheric carbon dioxide into the oceanic carbon dioxide, which is of equal magnitude. So let's return to this idea that there must be a return flux of carbon dioxide to the atmosphere and oceans to offset this outflow. This balance, which is in essence the long-term inorganic carbon cycle, has come to be known as the carbonate-silicate geochemical cycle. After inorganic carbon is involved in chemical weathering and carbonate mineral precipitation and is removed by sedimentary burial, plate tectonics provides the needed return flux of carbon dioxide in the form of metamorphic and volcanic carbon dioxide inputs to the atmosphere. Mantle-derived carbon dioxide is released to the ocean-atmosphere system at mid-ocean ridges and along convergent margins. This carbon is derived from the mantle and so is in a sense new. At convergent plate margins, the deep sea trenches, some of the sediments resting on the down-going slab here are subducted along with the plate. The plate and its sediment cover are carried to depths as great as hundreds of kilometers within the mantle. Down here, where high temperatures and pressures promote chemical reactions that transform the sediments into metamorphic rock, the carbonate metamorphism that I'll speak about in just a little while. Among these reactions is the reaction between sedimentary carbonate minerals and silica-rich sediments that forms silicate minerals and releases carbon dioxide. Okay, we have the limestone, the calcium carbonate, the silica forming the calcium silicate and carbon dioxide. This process is termed carbonate metamorphism. If sufficiently high temperatures are reached at depth during carbonate metamorphism, magmas are generated. These magmas may erupt in volcanoes at the surface, releasing carbon dioxide to the atmosphere. Together, silicate weathering, carbonate precipitation, and ocean-atmosphere exchange are the reverse of carbonate metamorphism. Notice that this reaction is the reverse reaction of the sum of the three reactions involving silicate weathering, carbonate precipitation, and ocean-atmosphere exchange. Without a fairly close balance between the inflows and outflows of carbon, the supply of this important greenhouse gas to the atmosphere and ocean would, on geological timescales, quickly be depleted. Earth would soon become a frozen ball of ice. That may have been the fate of Mars, which appears to once have had flowing water on its surface and perhaps a carbon dioxide-rich atmosphere with a stronger greenhouse effect. In contrast, on Earth, the release of carbon dioxide after carbonate metamorphism and volcanism has essentially balanced the consumption of carbon dioxide during silicate weathering over the history of the planet. What has ensured this balance? We cannot call on simple chemical equilibrium because the reactions involved are representative of a whole host of processes rather than a single chemical reaction. Rather, we must look for feedback loops that, according to the amount of carbon dioxide in the atmosphere, adjust the rates of carbon dioxide input by volcanism or of carbon dioxide removal by silicate weathering, and thereby keep the reservoir at steady state. Because it is driven largely by heat flow from Earth's interior, the rate of volcanism is probably not very sensitive to either the amount of carbon dioxide in the atmosphere or to the climate of Earth's surface. In contrast, many climatic factors affect the rate of chemical weathering. The regulation of atmospheric carbon dioxide on long timescales, that is millions of years, likely is a consequence of the feedback between climate and the rates of silicate weathering. The climatic factors that help regulate the chemical weathering rates of silicate rocks include temperature. Remember, rates of reactions, including chemical weathering, tend to increase as temperature increases. And also rainfall. Weathering requires water as a medium, both for the dissolution of minerals and for the transport of the dissolved minerals to the oceans, and thus weathering rates rise as precipitation rates increase. So notice in this diagram, what I'm saying here is the surface temperature, there's a positive coupling here. Normal arrowheads indicate positive couplings, these circular arrowheads indicate negative couplings. So an increase in temperature increases the rate of silicate weathering. Increases in rainfall increase the rate of silicate weathering. But what is happening between silicate weathering and atmospheric carbon dioxide? Well, as we saw, silicate weathering, if we increase that rate, it will reduce the amount of atmospheric carbon dioxide. It is a sink for carbon dioxide. But if we reduce the amount of carbon dioxide, we will reduce the greenhouse effect. Notice that positive couplings, if I reduce this, I reduce this. If I increase this, I increase this. The effect is proportional. With negative couplings, the reverse is true. If I reduce the silicate weathering, I increase atmospheric carbon dioxide. If I increase silicate weathering, I decrease atmospheric carbon dioxide. Of course, if the greenhouse effect is reduced, we get a reduction in surface temperature. And now we've formed ourselves a negative feedback loop. Let's see how this works altogether. Let's consider what would happen if, for instance, surface temperature increases. If surface temperature increases, this would have two effects. It would increase the amount of rainfall because surface temperature would mean there would be more humidity in the atmosphere. Because you've got increased rainfall, you get more silicate weathering. And the silicate weathering is also increased because of the increased temperatures to begin with. But the increased silicate weathering is going to lead to a decrease in carbon dioxide. The decrease in carbon dioxide leads to a decrease in the greenhouse effect, which will then mitigate that original temperature increase. And so we formed our feedback loop, our negative feedback loop, where the increased silicate weathering rates tend to reduce atmospheric carbon dioxide levels because silicate weathering uses up carbonic acid. The overall feedback loop is negative. The feedback tends to stabilize Earth's climate against perturbations. To finish this online lecture then, let's summarize what we've learnt. The global carbon cycle involves processes that occur on land and in the oceans and involve both biological and non-biological chemical reactions. The organic carbon cycles operate on a variety of different timescales. On the short timescale, say from tens to hundreds of years, we see carbon dioxide removed from the atmosphere during photosynthesis on land and returned during respiration. A small amount of terrestrial organic carbon survives respiration and decomposition and is buried in sedimentary basins on land or is transported to the sea. In the oceans, phytoplankton produce organic matter that is consumed by zooplankton and decomposed by aerobic and anaerobic bacteria. A small fraction of the organic matter settling through the water column is not decomposed and is instead buried in marine sediments. On longer timescales, say millions of years, organic matter is buried in sediments that have undergone lithification. When organic matter concentrations are very high in the sediment, fossil fuels may form during burial and lithification. The sedimentary rocks may eventually undergo uplift through tectonic processes, which will lead to exposure and weathering. And during that weathering, organic matter undergoes oxidation, producing carbon dioxide, which escapes into the atmosphere. An inorganic carbon cycle involving oxidized forms of carbon is important on both short and long timescales. Atmospheric carbon dioxide exchanges with carbon dioxide dissolved in the surface ocean on a timescale of decades. The uptake of carbon dioxide is enhanced by reactions among the forms of dissolved inorganic carbon in seawater. Atmospheric carbon dioxide dissolves into rainwater, creating an acidic solution. When rain falls on land, reactions with carbonate and silicate minerals convert carbonic acid to bicarbonate ions, which are carried to the oceans. In the oceans, carbonate-secreting organisms use the bicarbonate ion in the construction of their shells and skeletons. This material may dissolve in transit, or it may become part of the sediment that covers the sea floor. The regulation of atmospheric carbon dioxide on long timescales is a consequence of the feedback between climatic factors and the rates of silicate weathering as part of the long-term inorganic carbon cycle. The terrestrial and marine organic carbon cycles, the organic and inorganic carbon cycles, and the carbonate-silicate geochemical cycle are inextricably linked as parts of the global carbon cycle. This is the end of part 6 and the end of today's online lecture.